Yes, welcome back guys to this session. Welcome back on this India's largest e-learning platform, Gradeup. So guys, today we are having the second session of material science. Yesterday we have started material science for engineering services paper 1. And guys, you must be aware of that without qualifying paper 1 individually as well as qualifying the complete paper 1 plus 2 technical, you need to qualify overall also. So paper 1 plays a very important role. J Kumar, hello, good morning. Yes. So guys, yesterday we have just started the crystal structure. So I'm intentionally putting these slides also in front of you so that I can give a quick revision to those who have not attended. So let us start the session guys. Please like, share and subscribe so that others can also reach to this wonderful platform. And please tell me, am I properly audible, visible to all of you or not? I told you the weightage, my dear, for material science. The weightage is around, it is going to be from 11 to 14 questions are coming. In 2018, the number of questions were quite high. Okay, otherwise, generally 11 to 14 questions you can ask. So you can expect. So my dear, one question is for 2 marks. Okay. Yes, Prakash, good morning dear. Rinkesh, good morning. Let us start it guys. So now let us start. So as I already told you that this is our expectation and that depends on property. Property depends upon structure. Structure depends upon manufacturing process, alloying element and treatment. Then my dear, I also told you about the property. Properties are the quantitative indices, means some numbers you are giving. Fine. Means some number you are giving. That number is given to the behavior of material that we have yesterday covered, and that is whenever it is subjected to external loading. There are 3 levels of structure: macro, micro and crystal. So I am just revising yesterday what we have discussed. Macro level are giving us the properties which depends upon the surface ones, like nodes will reduce ductility, sharp corners will reduce the fatigue strength. Not sharp corner exactly, the abrupt changes of cross section. Okay, that is something in reducing the fatigue strength. Then I told you about microstructure. Microstructure consists of grain boundary, grain orientation, phase boundaries. I have given you an example of laddu also. Then I told you, my dear, about crystal structure. They cannot be seen, they can only be observed under X-ray diffraction experiment. I told you about the types of material. One is crystalline, other is amorphous. I also told you, my dear, whenever we are talking about the crystalline material, the materials which are having 3-dimensional long-range periodicity, 3-dimensional long-range periodicity of atoms, molecules and ions, and they are said to be crystalline materials. And my dear, they are metals, polymers, ceramics. These are the examples of the type of material. Okay. Then my dear, amorphous materials are those which are not crystalline. Example was glass. I have also given you an example of metallic glass, if you remember. That is made up of metal, but it is having characteristic of amorphous. Our syllabus is related to crystalline material. We need not to go for amorphous ones. Then we started about crystalline materials. Then I told you, my dear, that when we are talking about crystalline material, actually then we have discussed about that a crystal structure consists of crystal system and Brevis lattice. Then I told you crystal system tells you the shape and size of the unit cell, and Brevis lattice gives you the arrangement of atoms in the unit cell. All these things we have discussed earlier in the yesterday's class. Now my dear, our discussion is going to move forward. Now we are going to start about different systems. Total there are 7 crystal system and 14 Brevis lattice. I will say total there are 7 crystal systems. 7 crystal systems. 7 crystal systems and 14 Brevis lattice. 14 Brevis lattice. And my dear, in 7 crystal system and 14 Brevis lattice, all engineering materials are going to be covered. Every material is going to be covered in this 7 system and 14 Brevis lattice. Whenever I tell this thing to the student says, sir, why that atoms, molecules, those materials are available in 7 crystal system and 14 Brevis lattice. Why not only one crystal system and one arrangement of atoms is enough? Why so much number of arrangements are possible? Why so much number of systems are possible? So my dear, I would like to say, like if I ask you, all of you are sitting in your home, you are looking the lectures, you are studying. So my dear, if I ask you whether all of you are in the same sitting arrangement or different sitting arrangement, you will be saying, sir, maybe different, maybe some of you will be sitting like this, some of you will be sitting like this, some of you may be writing the notes, whatever I am teaching. So all of you will be sitting in different arrangement. So my dear, you all will not be same. You all will be different arrangement. Then if I ask you why these much arrangements are possible, you will be saying, sir, everybody feels comfortable in different arrangement. Like some student may feel comfortable while sitting like this. Some may feel comfortable while sitting like this. Some may feel comfortable like lying on the bed. Yes. So based on your comfort level, you guys will be there. So my dear, same is the case here. When we are going to say same is the case here, when I am saying here, also when you see the atoms and molecules, my dear, atoms are having different sizes, different atomic number and different atomic sizes. So why, when we are saying different sizes, I would like to say different number of electrons are available with them. If you are considering two atoms, my dear, all the atoms have one nucleus which is positively charged, and electrons are available which are negatively charged in an atom. Okay, so when you are going to have positive and negatively charged particle, if you are having two atoms, then you will be taking those two atoms near to each other, my dear. Then obviously positive will repel each other, negative will repel each other, same charges repel and opposite charges attract. So when two atoms are going closer to each other, then nucleus will repel each other, electron will repel each other, and electron nucleus will attract each other. So there are some attractive and some repulsive forces present between two atoms. So when two atoms are coming closer to each other, repulsive forces increases, attractive forces reduces. When two atoms are going away from each other, attractive forces increases and repulsive forces reduces. So in this way, my dear, the forces will increase or decrease. So when they are coming closer, repulsive increasing, going far away, attractive increases. And my dear, there is a difference, there is a distance between the center of atoms known as bond length distance. Bond length distance is the distance between two atoms at which atoms feels most stable condition. They feel most stability. They feel stability. So my dear, that distance is known as bond length. So atom always want to be at that distance where they feel more comfort. So they will try to achieve that position where they will be feeling most comfortable. Okay. So that condition is the bond length. So my dear, based on their sizes, different atomic numbers, different attraction and repulsions are there. And because of that only, my dear, different sitting arrangements of atoms are giving them stability. So all the atoms, all the materials shows different system and different Brevis lattice. You know, crystal system was nothing but shape and size. Shape and size of unit cell. Shape and size of unit cell. And you know that Brevis lattice is nothing but arrangement of atoms. Okay guys, so 7 crystal system, 14 Brevis lattice. In this every material will be covered. Good morning Shri, Vanilla. And here I would like to say now, be regular in the classes if you really want to learn. I can guarantee you that we will be giving you proper whatever is required for paper 1, and the content will be unmatchable from anywhere else, and you will be enjoying and able to solve all the questions. But for that you need to join on the regular basis. Okay guys, so now we are going to start it, and I will be going for some of the characteristics, but before that let us define some of the things. As you know, some basic definitions are there. There is one basic definition is unit cell. When we talk about unit cell guys, unit cell is an arrangement of atoms It is the simplest arrangement of atom which when repeated for infinite number of times in all the crystallographic axes will give you crystal lattice. When you are going to say unit cell, my dear, let us say first of all, I am coming on to the simple unit cell, simple cubic. You know, cubic means A is equals to B is equals to C, alpha is equals to beta is equals to gamma is equals to 90 degree. If this condition satisfies, it is cubic. And when I am saying simple means only 8 corner atoms will be there. Yes. So if you are going to say that this is a unit cell, if it is a simple cubic unit cell, you will be showing the atoms like this. Only corner atoms will be there, no face center, no body center. So this kind of thing is known as simple cubic unit cell. So this is the simplest arrangement. Dear, सब कुछ 10 से 20 नंबर के सब कुछ लगभग जो आता है वो मैं बोलूंगा कि 5 to 15% का वेटेज कवर करता है. तो 10 से लेकर 30, 10 to 30 मार्क्स का वेटेज रहेगा करंट अफेयर्स का. ओके, यस, 10 to 30. So my dear, this is the simplest arrangement of atom. If you are going to repeat it in the 3-dimensional crystallographic axis, like this is x-axis, this is y-axis, this is z-axis. So when you are going to repeat it in all the crystallographic axis, then you will be getting a 3-dimensional crystal lattice. So my dear, you will be having the complete material once you will be repeating it in the 3-dimensional crystallographic axis. Okay, so this is a unit cell. So unit cell is, my dear, nothing but the smallest group of atom. Okay, it is nothing but the smallest group of atom. It is nothing but the smallest group of atoms. When this smallest group of atoms is going to be repeated in 3-dimensional, 3 crystallographic axis for infinite number of times, it will result into crystal lattice. It will result into crystal lattice. And guys, if you want to see what is crystal lattice, I am showing you the crystal lattice also. And guys, I will be showing you the crystal lattice. Yes. If you see this structure, just look at it. You can see this is a unit cell. You can feel, just feel it, that this is a kind of unit cell. This is a unit cell. And when this unit cell is repeated, you can see it has been repeated to backward, to right side, even it can be repeated for left hand side. So this is said to be crystal lattice. So my dear, this complete is said to be crystal lattice. So crystal lattice is very giant in size, very big in size, and it is made up of infinite number of unit cells. So if you are going to repeat a unit cell in all that 3-dimensional space, and my dear, you will be getting the complete crystal lattice. Now my dear, this is said to be crystal lattice, and you can feel one thing, that in crystal lattice what we are showing exactly. We are showing a structure made up of lines. I am telling you how and what I want to say. I want to say this point. If you see this, my dear, reality is this. In reality, atoms are touching each other. If you see, the atoms are touching each other. Like these are 2 atoms, these are 2 atoms. So atoms are touching each other. Then how we are showing these lines? So guys, these lines are, if you are talking about these lines do not exist in real. These lines do not exist in real. These lines we are just making for the sake of making the calculation easier. So when you are talking about these lines we have plotted only to make the calculation easier. Otherwise, these lines are not present in reality. In reality, these atoms are there in 3-dimensional space. So my dear, the reality is these atoms. This is the reality. And this reality can be shown by 2 ways. One is known as crystal lattice or line lattice. When I am saying crystal lattice or line lattice, what does that mean? When you are showing a unit cell with this geometry, then my dear, this you are showing only with lines. which are hypothetical lines. These are just for the sake of calculation. So here you show atoms like this. Otherwise atoms are not that smaller, atoms are bigger one, and those atoms are touching each other. Here you are not showing the touching. Exact condition, if you want to see this ABCD plane, in reality how this ABCD plane will look like. So guys, we are just teaching you as we teach in the classes. It is not like we are just teaching some part. I am teaching you in a complete field way so that you can feel it. If you are able to feel it, then it is very easy for you to remember the things. Reality is this one, but you are showing it this one. So this is said to be the crystal or line lattice when you are showing by the line. But that line lattice I am saying for the 3-dimensional view, when you are going to make in 3 dimension repeatedly infinite number of times. Yes. But mind you, there is another way where we do not even show the lines. When we are do not showing the line, we are just showing the atoms. And that atoms are also not shown like this view. If you are showing the atoms just by a point, then the same structure can also be shown like this. If I am just removing the line, just imagine, if I am removing the lines, I will be left with these 8 corner atoms like this. And this kind of view is said to be the space lattice. So if we are showing the atoms by dot and we are not showing any line lattice, we are not showing any lines, it is said to be space lattice. In other words, if for a crystal or line lattice, if I just remove the lines, it becomes line lattice now. So now it becomes it becomes space lattice. If you want to make the line lattice, you need to join these lines. When you are joining this, it will become line lattice. When you are removing this, it will become space lattice. But my dear, neither this is reality nor this is reality. Reality is this one. Okay. In real, atoms are there, lines are hypothetical. Guys, please tell me, are you getting the things I am giving you? This is how we define the basic terminology. I defined unit cell. I defined already unit cell. I defined crystal lattice. I defined line lattice. I defined space lattice. And now I am coming on to the next thing. Obviously, this view is better than this, because by looking at this, you cannot tell which atom is lying in the front plane, which atom is lying in the back plane. Here you cannot tell which atom is lying in which of the plane. By looking at this, you can tell that which atom is lying in which plane. Okay, so this view is more clear than this view. That is true, my dear. That is for sure true. Yes. Okay, so guys, when we are talking about after this, there is one more definition I will be telling you. That is nothing but yes guys. Okay, so I am coming on to that. One more definition is, my dear, that is when you are talking about lattice parameter. Lattice parameter is nothing but when you are going to make a line lattice. Then, my dear, this side A, B, C. So this A, B, C, they are said to be lattice parameter. Okay, my dear. So this is the next definition. So we have seen one by one all the definitions. We have seen. Now, my dear, we are coming with the characteristics of unit cell, the very first topic from which questions are to be asked. So, my dear, we are going to start the very first topic from which the question will be coming, and that topic is nothing but the characteristics of the unit cell. Characteristics of the crystal structure. Characteristics of unit cell. And my dear, the first characteristics we are going to see is A to R ratio. Here A is the lattice parameter, A is, my dear, lattice parameter, and R is the atomic radius. So, my dear, first of all, we are going to make a relation between these two things, and for that we need to discuss different geometries. Like we need to consider simple cubic, we need to consider face centered, we need to consider body centered, we need to consider hexagonal. So my dear, we are going to see one by one. First of all, my dear, I am coming on to the simple cubic structure. Yes, we are having all the figures with us and we have also seen before. So when I am coming on to this, my dear, this is a simple cubic structure. If you see this structure, my dear, this distance is A, known as lattice parameter. And my dear, this is the atomic radius, this is the atomic radius. So by this you can definitely write A is equals to 2R. So my dear, A is equals to 2R is A to R ratio. If you want to find out, then A to R ratio will be coming out to be 2 for a simple cubic unit cell. So for simple cubic unit cell, the ratio of A to R is going to be 2. My dear, this is a very important parameter because that will help you to tell about the density variation. It will help you to find out the density variation. And when I am saying about the density variation, what do you mean by that? My dear, what do you mean by density variation? Dear, I would like to say there is a property known as allotropy. Allotropy is nothing but, my dear, different materials shows different crystal structure at different temperature and pressure. Different kind of material shows different crystal structure at different temperature and pressure. Like iron sometimes becomes BCC, sometimes becomes FCC, sometimes becomes BCC, sometimes becomes FCC. So when iron is changing its crystal structure at different temperature and different pressure, then I would like to say that iron is said to be allotropic iron. When somebody shows different crystal structure at different temperature and pressure, it is said to be allotropic. So iron is allotropic iron. And my dear, as the temperature will change, as the pressure will change, crystal structure will change. And when crystal structure will change, A to R ratio will change. If A to R ratio will change, density will change. So that is why I said density is a function of A to R ratio. Okay, first thing. Now my dear, for simple cubic it is 2. Let us find out for other geometries also. Now this geometry is body center cubic. You can see in body centered, as the body center atom makes entry. If you see, yes, good morning Rajan Kumar. As I have shown you in the simple cubic, my dear, you can see atoms are touching each other. Like these two atoms are in contact, these two atoms are in contact, these two atoms in contact, these two atoms in contact. Okay, so likewise atoms are in contact like this. Atoms are like in contact like this. Yes, but my dear, as one atom will be entering in between them, my dear, if one atom will make entry in between them, all these atoms will get separated out. So this and this atom was in touch in simple cubic, but because of this atom, these two will leave contact, 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 these two will leave contact. So every atom now will get separated because of that center atom. So body center atom will make all of the atom to be discontinued to be in contact. So all of the atom now leave the contact. And guys, if you want to find out A to R ratio, you need to consider the atoms which are in contact, because now if you consider this distance to be A, you consider this distance to be R, you don't know this distance now, so we cannot take this side to find out the relation. We need to consider the atoms which are in contact, then only we can find out, my dear, A to R ratio. If you see this corner atom, this body center atom and this corner atom, they are in contact. I need to say this corner atom, this body center atom and this corner atom, they are in contact along this diagonal. They are in contact along this diagonal. They are in contact along this diagonal like this. And my dear, if you want to say, let us say this diagonal is AC. So if you want to see this AC will be like this. This is a corner atom, this is a body center atom and this is again a corner atom. So this is how it looks like. So my dear, these are two corner atoms and this is the body center atom. So you can also imagine if there is a room. In this room, all these atoms are present at the corner. This body center atom is in contact with all the atoms. So you can also consider either this, or you can also consider this atom and this atom. They will also be in contact. So always opposite diagonals, like this atom and this atom will be in contact. Like this atom and this atom will be in contact. So my dear, this is how the atoms will be in contact, because the body center atom will be in contact with all other atoms. Okay, so if that is the case, you know that if this side is A, in cubic A, B, C are same, this side will also be A, this side will also be A. So if all of them are equal, it is very much obvious that it will be root 2A. This will be root 2A by Pythagoras. And my dear, if this is root 2A, this is A, this is nothing but root 3A. Again by Pythagoras. So if this is root 3A, my dear, you know, this is radius R, this is radius 2R, this is radius R. So from this to this, it is 4R, but it is also root 3A. So my dear, if both are equal, you can definitely write root 3A is equals to 4R. And my dear, if you are going to find out A to R ratio, it will be coming out to be 4 by root 3. A to R ratio is 4 by root 3. A to R ratio is 4 by root 3. And my dear, this is the A to R ratio for body centered cubic. So for body centered cubic, the ratio is going to be 4 by root 3. So 4R by root 3 is A to R ratio. And my dear, these kind of question you will be expecting in your paper, engineering services paper 1. So guys, if you really want to study, if you really want to qualify paper 1, guys, in this series we will be covering the complete syllabus of paper 1 before your examination. We have properly planned it and you will be getting the complete schedule within 2 to 3 days over the Telegram channel. So just join us on the regular basis on this channel for this ESE paper 1. We can guarantee your selection because we are dealing all the things in a manner like you will be getting the content related to paper 1, which no other platform will be giving up to that much quality. So guys, don't miss the opportunity. Okay, if gate have been gone, if it is good, then also ESE is a dream job. If it was bad, then ESE is one of the way to achieve something big. So my dear, now this is A to R ratio for body centered cubic. Now we are going to discuss about the face centered cubic. Now we will be discussing about the face center cubic. Okay guys, so when we are going to talk about the face center cubic, in face center cubic, my dear, it is going to be like this. In face centered cubic, it is going to be like this. My dear, it is having the corner atoms. It is having the corner atoms at each of the corner. At the same time, it is having face center atom on this face, on this face, on this face, on this face, on top, on front. So every face is having a face center atom. So if you see, here are 8 corner atoms, 8 corner atoms plus 6 face centered atoms. So 8 corner atoms plus 6 face centered atoms. So my dear, when we are having corner atoms as well as face centered atoms, yes. So my dear, this is something you are having the structure to be FCC, face centered cubic. Once again, I would like to say, my dear, like this is A, this is B, this is C, this is D. Yes, Rajan, do you want to ask something? Do you have any query? If that is the case, you can please ask. So my dear, if I say for simple cubic, if you say ABCD face for simple cubic, and if you see ABCD for FCC, I am showing you the difference. My dear, when you are going to say ABCD for simple cubic, you know that it is having only 4 corner atoms and all the corner atoms are in contact like this. But when we are talking about face centered, my dear, for face centered, there is a face center atom coming at the face. So because of this face center atom, this will be a corner atom, this will be another corner atom, this will be another corner atom, this will be another corner atom. So this face center atom will be giving those atoms apart and it will leave the contact. My dear, you can see the contact is nowhere between the corner atoms because of the face center atom. So my dear, this time you can see this atom and this atom are in contact. So to find out A to R ratio, we can definitely use this diagonal. And my dear, you know very well that this is side A, this side is A, है ना? this side is A. So obviously if you want to find out this side, by Pythagoras it is going to be equal to root 2A. So if it is going to be root 2A, my dear, so this is R, this is 2R, then this is again R, and this distance is root 2A. When you will be equating it, my dear, you will be writing 4R to be equal to root 2A. So my dear, A to R ratio will be coming out to be 2 root 2. It is coming out to be 2 root 2. So my dear, we have found out A to R ratio for simple cubic, for FCC, for BCC. I am deriving in front of you so that if question comes, you must be in a position to answer very easily. So my dear, whatever we have calculated in today's class right now, first of all, we have done it for simple cubic and we have seen A to R ratio. It came out to be 2 and the example for simple cubic is polonium. Polonium is the example which is found to be in simple cubic structure. My dear, then we are talking about FCC. For FCC, A to R ratio is going to be 2 root 2. They may ask you in increasing order of A to R ratio or decreasing order of A to R ratio. That kind of question are expected in engineering services paper 1. So my dear, when you are going to have the example of FCC structure, you will be saying the materials like aluminium, yes, like gold, silver, gold, yes, and my dear, also iron in the temperature range of 910 to 1450 degrees Celsius. In this range it is found to be FCC in nature. And my dear, after that if we enter into the BCC elements, then my dear, BCC elements are having A to R ratio is equal to 4 divided by root 3. So my dear, if you are talking about BCC, the example is tungsten, vanadium, chromium. And my dear, when we are talking about these as an example, I would like to say that, my dear, if you are talking about iron is BCC except the above range. So I already told you some atom, some material is changing its crystal structure from BCC to FCC. When change of temperature and pressure is there, it is said to be allotropic. So it is allotropic iron, my dear. So when we are talking about this, you can see the examples may be asked in the paper. Even for mechanical engineering student, they were coming in the technical paper. So obviously they can come in ESE paper 1 also. So my dear, when we are talking about this simple cubic FCC, BCC, if you are going to see, these are examples. This is A to R ratio. As I said, one question may be write the increasing order of A to R ratio or decreasing order of A to R ratio. And guys, A to R ratio is something which is going to define the density. If A to R ratio will be changing, the density of the crystal structure will surely change. And one more thing I would like to say, my dear, simple cubic are not in measure of the application of engineering, so we will never talk much about simple cubic. Our main discussion will be about FCC and BCC. If you want to know the properties of FCC and BCC, my dear, then FCC are found to be strong and ductile. FCC are found to be strong and ductile. At the same time, my dear, BCC are found to be hard and brittle. BCC are found to be hard and brittle. Okay. So these are the properties associated with BCC and FCC structure. And in the next 2 classes, I will be deriving why they are found to be hard and brittle, why they are found to be strong and ductile. But that is for sure, if somebody is having some property, it always have that property with itself. Like if I say that if I am a person who is having more anger, then wherever I will go with my anger only. So my dear, similar to that, if these materials are having hardness and brittleness more, so wherever they will go, they will be having that hardness and brittleness along with them. So wherever they will go, they will be having the hardness and brittleness with them. So my dear, they are also found to be carbide forming. So whenever you are going to add, my dear, whenever you are going to add them with the steel, in the steel carbon is always present. So they will be just reacting with the carbon and they will be making the carbides. And carbides are the forms which are said to be, obviously they are found to be hard. So my dear, that's the reason whenever they are added, They make tungsten carbide, they make vanadium carbide, they make chromium carbide. Tungsten, whenever it makes the carbide, tungsten carbide is going to increase the wear resistance. Is going to increase the wear resistance. And my dear, at the same time, when we are going to make vanadium enter, vanadium will make vanadium carbide, which will increase the fatigue strength of the material. And my dear, chromium carbide will increase the corrosion resistance of the material. So whenever BCC elements are added in the steel, they are going to improve these kind of properties. That's why BCC elements are added to improve the properties in the FCC elements. As BCC elements are found to be hard and brittle, if they are added into FCC material, they do not allow FCC to expand much, and because of that, my dear, they just try to reduce the grain sizes. I will be telling you what is grain size, and because of the reason, BCC elements are said to be grain size refiners. This is a very, very important point, guys. They are said to be grain size refiners. This is even question asked in interviews, that why BCC elements are said to be grain size refiners. And this question can be asked from any branch students. And when you are going to say this is grain size refiners, you might want to know the reason behind that. So I am going to tell you the reason behind that. Let us say, my dear, you are having a container, and in this container, let us say some molten metal is there. In this container, let us say some molten metal is there. In this container, let us say some molten metal is there. So my dear, you know that this is molten metal. Obviously, this molten metal will be in the hot state and the walls are in the cold state. So what happened is, due to this cold walls, some solidification front starts. Solidification fronts start. What do you mean by solidification front? Means that liquid starts solidifying. Liquid starts solidifying like this. So when liquid starts solidifying, my dear, if you are going to put some BCC element in between, then my dear, BCC elements are found to be hard and brittle. They will not allow this solidification front to move further. So when they will be stopping it, obviously from here new solidification front will come on. So because of this, if you are going to see the structure after solidification, you will be finding out small grains like this. Small grains like this. Grain is nothing but a solidified front. But my dear, if you are not adding the BCC element into that, you may have very big size grains like this. Okay. So this is said to be fine grain structure. This is said to be coarse grain structure. And this you are getting because of BCC elements. That's why it is said to be, BCC elements are said to be grain size refiner. So it is a fine grain structure. This is a coarse grain structure. So we are getting fine grain structure because of the application of BCC elements. So BCC elements are said to be the grain size refiners. So my dear, that's why BCC elements are said to be grain size refiners. Now guys, I am coming on to the second property, that is average number of atoms. Okay, and that is a very important question and it may come in examination regularly. So we are talking about average number of atoms in a unit cell. So my dear, the point is, whenever we are talking about average number of atoms, you have seen in simple cubic, all the 8 corners consist of 1 atom each. So 8 corner atoms are there. But my dear, when we are talking about the 8 corner atoms, those corner atoms are not like one unit cell can use it. No. That atom at the corner is shared by many unit cells. Like if you are going to see, I have already shown you one figure. I am again going back to that figure, because that is only the benefit when I am teaching on smartboard. I need to show you the view so that you can have a clear picture that where these are going to be used. First of all, I would like to show you that. I am showing you that. I am just coming on to that. Just wait guys. So yes, this is the figure. This is the figure. If you see this figure, my dear, if you see this figure, it is very much clear in this figure that you can see this is a corner atom. and this corner atom is shared by this unit cell, these are two unit cells. Then this unit cell, these are four unit cells. And then horizontally this unit cell, horizontally this unit cell, this unit cell and this unit cell. So you can see overall 8 unit cells are using this one corner atom. So one corner atom is used by 8 unit cells. So one corner atom is used by 8 unit cells. Similarly, if some atom is present on this phase, this is shared by top unit cell and bottom unit cell. So one phase center atom is shared by 2 unit cell. But if some atom is present inside the body, that cannot be used by any other unit cell. So my dear, I would like to say that if that is the case, I would like to tell you, my dear, that a corner atom is shared by 8 unit cell. A corner atom is shared by 8 unit cells. A corner atom is shared by 8 unit cells, and a phase center atom is shared by 2 unit cells. Body center atom is shared by 1 unit cell. So my dear, if you want to find out the formula of average number of atoms, it is given as corner atom is shared by 8 unit cell. Phase center atom is shared by 2 unit cell. Body center atom is shared by 1 unit cell. So my dear, if you are going to define it here, NC is said to be number of corner atoms. Number of corner atoms. Okay. NF is said to be number of face centered atom. Number of face center atoms. And Ni is said to be number of body centered atoms. Okay guys, and with this you can find out the average number of atoms in a unit cell. And one by one I am finding out in front of you. Let us say guys, we are having the unit cell said to be simple cubic. If you are going to have a simple cubic unit cell, my dear, in simple cubic unit cell, corner atoms are 8, face center atom is 0, body center is 0. So you will be having the average number of atom to be equals to 8 by 8 is equals to 1. Then my dear, if you are going to repeat this for body center, if you are going to repeat it for body centered cubic, then my dear, you will say the corner atoms to be 8, face center to be 0, body center to be 1. You will be finding out the average number of atom to be 8 by 8 plus 0 plus 1 by 1. It will be coming out to be 2. And my dear, third one is going to be face centered cubic. You know, corner atoms are going to be 8, face center are going to be 6, body center is going to be 0. If you find out the average number of atoms here, you will be getting 8 by 8 plus 6 by 2 plus 0. So my dear, this time if you are going to find out, you will be getting it to be 1 plus 3. The answer will be coming out to be 4. Okay. So here it is 1, here it is 2, here it is 4. So this is how we are, very good Sajal. So here this is how we are going to find out the average number of atoms. My dear, in engineering services paper 1, you can have a question like write down in the increasing order of average number of atoms. There they will give you all simple cubic, body center and face center. So this type of questions are more coming in ESE paper 1. That's why I am calculating each and everything in front of you guys. So we have done 2 characteristics today. One is we have seen about A to R ratio. Second, we have seen about average number of atoms in a unit cell. Okay. And guys, in the next session we are going to see, my dear, we are going to see about the coordination number, about the atomic packing factor, about the ductility brittleness. All these factors will be coming in the next session tomorrow 11 a.m. And my dear, after that we will be studying about Miller indices of planes and direction. So my dear, next 2 classes are very important, and with that we will be completing the crystal structure. Then we will be entering into the crystal defect part, and one by one we will be completing the syllabus of material science. Then after that, project management and other subjects will come. We will be completing the syllabus of ESE paper 1 much before the exam, don't worry. And then we will be having some mock test also, as we have done in the gate part. Okay. So guys, this is something we have discussed today. So I would like to say, keep revising these things, because these things are going to be there in the examination again and again, and you must be prepared about this. Okay, once again I can show you the complete structure. If you see, this is for simple cubic, body centered, face centered, and this is the atomic arrangement in simple cubic, body center, face center in the atomic view. So these are the three things you can see. And guys, this is okay for today. Madhav sir, your class notes is sufficient. Dear, my class notes are going to be much more than what is required. Even they are sufficient for the mechanical student for their technical paper. Okay. Yes. So don't worry about that. And even we will be sharing this PDF in the Telegram channel. You just join our Telegram channel. I will be sharing the PDF there. So goodbye guys for this session. Thanks for joining again. And here I am saying goodbye to all of you for this session. We are meeting at 2 p.m. At the Mechanical Marvels for ISRO class. Okay. Yes, dear, this class will be at 11 a.m. Okay. And at 2 p.m. we are going to meet at the Mechanical Marvels. Okay. Sajal, don't ask these kind of questions. I do not remember this. Okay. So guys, now just I am showing you a 30-second video, because you must know that a wonderful thing is going on Gradeup Super. As you know, February Mela is going on. Those who are getting subscription, first of all, you are getting 50% discount. Then my dear, after that, you are also getting some exciting prizes. Every day one winner is getting this. And my dear, at the same time, you can access to all the batches present there with one subscription only. One green card will be giving you all the test series. Okay. If you are getting rank 1000 to 2000 civil option paper, no dear, no chance. No chance, Shubham. No chance in that rank.
Hello students, Gradeup is happy to announce the February Mela, जहां आपको मिलेगा मौका to win attractive prices worth ₹50 lakhs on the purchase of Gradeup Super. आज ही Gradeup Super के साथ अपनी एग्जाम प्रिपरेशन शुरू करें with 9 interactive courses and mock tests designed by the best faculty and experts, 24/7 doubt resolution and best study material. इसके साथ ही पाएं exciting prizes जीतने का मौका। तो फिर देर किस बात की? आज ही Gradeup Super को सब्सक्राइब करें।
And guys, on 28th of February, you are going to give a test also, that is GNST scholarship test. So you can give that test to get the scholarship also. Okay. And Vision 4 batch is already been started, as I already told you, from 15th of February. You can join there also. So goodbye guys for this session. Thanks for joining once again. Tomorrow 11 a.m. once again we are going to meet for the next session. Goodbye guys for this session. Okay, Sajal, I am taking at 2 p.m. on Mechanical Marvels for ISRO DRDO, at 9 p.m. and Mechanical Marvels for all the examination production is going on. Yes, Rinkesh, you can see on YouTube every day the person who is winning the prize, his name is announced on the YouTube. Okay, you can see. So goodbye guys for this session. So let's meet. Okay, goodbye.